Hello and welcome to this webinar on tense cable nets and grid shells for form finding with GSA. Meanwhile, form finding. What is form finding? Why form finding? Well, it's all about geometric optimization. The architects say that form follows function, but as engineers we actually know that form follows force. Now, with the majority of the building structures, the floors have to be level. There's not much scope for engineering optimization other than maybe choosing the lightest steel beam and so on. But when you come to sort of long spans, roof structures, bridges, etc., then there is plenty of scope there for you to make something elegant, something efficient, lightweight. An example, this is this fabric roof from the Eden project in Cornwall. Now, the thing about these lightweight structures is they resist the loads not through sort of inherent stiffness, but through their shape, through their pre-stress, and through large deflections. They are more flexible than your average building, but that is the way they work. Now, these lightweight structures have been around for a little while. I mean, this is an example from 1972. This is Frei Otto's Munich Olympic Games roof. And whilst not the first structural fabric structure, it's definitely a major landmark in the science of lightweight structures. And this is where you first get the architecture and engineering combining together to make some wonderful structures. Of course, this was nearly 40 years ago, and so computers were not anywhere near the same condition they are today, and so they had to rely almost entirely on the physical models to calculate the forms. Now we get on to compression structures, for example, columns. Columns just go straight up and down, not too much scope for creativity, but actually there is. Now here we have the crypt of the Colonia Güell Church in Barcelona, designed by Antonio Gaudi over 100 years ago. He was a master of form finding and structural efficiency. Now, obviously he didn't have computers to find the ideal shapes, so he used hanging chain models instead. He's most famous for the Sagrada Familia, the cathedral in Barcelona. Now we have photographs of the Colonia Güell model. We don't have the model for the Sagrada Familia because unfortunately that was destroyed during the Spanish Civil War, but we do have his drawings and so on. Obviously, if he had GSA in those days, he could have used that, but the end result, structural efficiency, compression only structures, and yet beautiful, organic, and such amazing contrast to, say, a Gothic cathedral where you have vertical columns and then need flying buttresses to keep everything stable. A slightly more recent example of a compression-only structure is the Pavilion of the Future from the 92 Expo in Seville. Now those are stone blocks, cast stone blocks, which are ungrouted, so they're just friction between those stone blocks and then held in place by the tension from those cables. And if you see the full height of that structure, it is ridiculously audacious. But its stability is down to getting the forces and the forms right. Another earlier example showing getting the form right, so you can do some amazing things. This is Robert Maillart's 1939 cement hall from the National Exhibition in Zurich. You can get an idea of the scale of this structure and the thinness of the concrete by looking at the man on the bridge. I think it's about 20 meters high and it looks about 50 mil thick. Not a lot to span that sort of structure, that sort of size span. So this is all down to the form. Now, the tension structures, you need to have the right form. The geometry is crucial. The surfaces have to be double curved for stiffness, because they can only take forces in tension, and therefore, depending on which direction the forces are going, depends on which aspect of the fabric takes up the load. There are three basic shapes, which are all, of course, variations on this double curvature idea: the conic, the barrel vault, and the hypar. Again, the forms, obviously you can see the double curvature of the barrel vaults there, but also the geometry of the arch is crucial. And this is a slender arch which is both supporting the cable net fabrics there and also is supported by the fabrics. Get the geometry right and the arch is very strong. Get the geometry of the arch wrong and it will buckle under load, or you need to make it very heavy duty. And this, of course, is the Avery in Hong Kong. Another important output from the form finding is the exact geometry of the fabric itself. So if you can see the seams on the Marseillaise sculpture from the Tate Modern Gallery. These individual panels have to be cut to shape, and when they're stitched together, they naturally form the resultant shape. And if you get it right, it looks right. If you get it wrong, it doesn't work. You get wrinkles and so on the structure. Another important output and also input to the form finding is the prestress. Now, the prestress is crucial to the form finding, both in terms of the balance of the prestresses, so you're balancing the fabric prestress against the cable edge prestress and so on, and that varies the end result in shape, but also how you achieve the prestress, whether it's through cables, whether it's through solid points and so on, and these all make a big difference to the final shape. And quite often with form finding, you are playing with the various prestresses to get the right shape. These prestresses have to then pass into the structure, and okay, the picture on the left is the Marseillaise whilst it's being erected, and you can see it's not at its design pre-stress, and so it is wrinkly. And if you get the pre-stress wrong, too much pre-stress in one direction, the other, you see it's up here, the pre-stress going vertically there, you get these called Huygens tension fields. You get waves in the fabric. Tension it up correctly, as it is on the right, perfectly smooth. Now, this pre-tensions and form finding also becomes useful for other structures, such as this Kurilipa Bridge in Brisbane, which is a tensegrity inspired structure. This was built over a busy waterway, and the site constraints and the contract constraints meant that there was very little, if any, opportunity to adjust the cable lengths once they were in position. So the engineers had to work out the pre-stresses and the cable lengths up front using GSA, of course, and it all fitted together very, very nicely. Now, GSA uses a special type of nonlinear analysis for this, which is we call dynamic relaxation. Well, the solver is called GS Relax, and it uses dynamic relaxation. It's a solver embedded within GSA. GSA has several solvers, linear, nonlinear, and so on. Some of the old hands may know of this as Fablon. It uses a method called dynamic relaxation, and this is then used for geometric material nonlinear buckling, and of course the form finding as well. The way it works is essentially it's like a vibration analysis, where you have a number of the structure is rendered as a series of masses, and you are after equilibrium. Now there are a number of unbalanced positions. There is an out of balance force in the structure, which of course then accelerates these masses. But we are looking for the equilibrium position where forces are all balanced. Note, of course, this is a dynamic and not a matrix method, so you can deal with some quite flexible structures. Again, as it's dynamic and not as dynamic analysis, you need to have some sort of damping in the analysis so that the model sort of converges onto the final geometry. GSA handles this damping automatically using a number of methods. Usually it works very well. Occasionally you might have to go in and sort of take control on the damping to help it converge. But most of the time the automation works fine. So the form finding itself. So form finding, as you might guess from the expression, is an analysis process to find the form, the geometry of the shape. So it's different to other analyses in that the results are not forces or moments. It is a new geometry. And GSA uses a choice of 3 different form finding methods: soap film force density and called normal properties, or ignoring form finding properties, and we'll go into these in a bit more detail in a minute. And you'll find that different methods have different advantages and for your particular structure. Also, a common thing to remember is the boundary conditions are very important for form finding. The fixed points, the edge conditions, these are the conditions which allow your structure to actually generate the pre-stresses. So typically you might have a fixed edge, such as the one on the left, which is coming from a beam or a foundation point or a holding down point and so on, or on the right hand side where you can see you've got a cable edge to the fabric. Note also that there's a cable embedded within the fabric in this particular case, and those can sometimes be useful. So soap film first of all. Soap film, it mimics real soap bubbles, and real soap films automatically find the minimum surface area or surface energy between say 2 fixed rings there. And unlike sort of straightforward a real soap film, GSA has both 2D soap film membranes, so 2D elements, but also 1D elements as well. So you can use this for cables and fabrics, and of course a combination of the two. Now, so the soap film you can imagine as a bubble, the cables you can imagine as elastic bands. Now these are during the form finding, these elements have a constant stress and zero stiffness, which means that the nodes are free to move around, and this means that to keep the structure under control during the form finding, we need to add in these special elements called spacers, and which do, as the name suggests, keep the nodes spaced out. Now spacers are quite unusual into the elements because one spacer is formed up of multiple spacer elements which all have the same property. They also have to be in the same direction and so on, which means that, as we see at the top, one spacer, several elements, but below, if those were the same property, those would be no good. GSA would reject these because one spacer is broken. Those will need to be 2 separate properties. Likewise, you cannot have any bifurcations in the spacers. And the analysis checks will actually flag up these. Now, as the GS Relax or GSA is a large displacement non-linear analysis, you only need to get the initial geometry right. I mean, you see in this high pass structure, we pin the 4 corners and have the edge cables, and the form finding does does the rest. Likewise for this barrel vault, for the arch parts, fully pin the nodes, which is purely for the form finding, whereas the cable is free to move, and the end result is the shape. Note also that the stresses in the NX direction, the bottom right diagram, the stresses are higher than in the NY. So this has been arranged so that the warp is going between the rings, and this is at a higher pre-stress than the warp going, than the weft going across. This is quite deliberate, and this balance of the pre-stresses affects the final form. Have an equal pre-stress, the saddle part will be much lower down. But forces, you can also use applied forces within the soap film methods. For example, if you want to do ETFE foil cushions, which are pressurized, you include that pressure load within the form finding, which and then gives you the pressurized shape. Can also use this for grid shell models and so on. One quite recent example, just 3 years ago, the water cube from the Beijing Olympics. The Olympics are quite a theme when it comes to this sort of structure. And you see, this is the ETFE foil cushions on the structure. Because ETFE yields under loads, the large cushions had to be form found first because they yielded too much under the load, and so they had to be form found and then cut to size before for the final pressures. The smaller panels didn't need that form finding, but again they still need the non-linear analysis to cope with the wind loads and so on. The end results, yeah, very interesting. Won, I think, at least 8 major awards. Another type of structure is the conic, and when you're modeling conics, you have to use a higher radial pre-stress than the circumferential pre-stress. Otherwise, the fabric tends to do what we call a neck. It collapses around about the middle here. Also note that the top structure is a ring, not a point. You can't do point supports in a conic form find. And here's an example, an unusual one, of the Museum of Modern Art in New York Liquid Skies exhibition from a couple of years ago. This is a mylar fabric, and obviously it's quite low tension. But you can see there the double curvature surfaces. You can see the edge cables, and you can see the toddler holding it down. Actually, it might just be in the way in the photograph. So let's have a look at GSA in action. Right, there we go. So I'm going to put together a high power fabric with backstays and struts. And to do this, I'm going to use the wizard. And this wizard is quite useful in this case because it creates the spaces for me. And I'm just going to make it 5 meters square. And I'm going to use ½ meter elements. I will set this up as a fabric. I will need to remember to create a fabric material when we get into GSA. And because these fabric elements have no thickness, they have no self-weight. So I'll just add in some self-weight onto the fabric. We'll need to include the spacers, and then spacers have the internal spacers, which are geodesic forms. These spacers make sure that the nodes remain on the surface of the fabric, and the surface is derived from the adjacent 2D elements. On the edge spaces, on the other hand, is obviously a bit more free to move, and you have a choice of bar or free. Bar is preferable in this case because it retains the pre-stress forces. If you're not worried about pre-stress forces, then you could go for a free spacer, and that can be more efficient, but obviously you don't get the end result. I'll also need the edge elements, and I'm going to edge this with a cable, which is going to be a tie element, and I'm just going to make it let's make it just a 10mm diameter cable and generate that. Maximize that. Let's have a look. So first of all, what I do is hold down the corners. So I'll just modify those two corners there and just pin them in position. These two corners here, I will pull those up by a couple of meters. I will move them up by a couple of meters. Don't copy them. That's better. Preview is a very useful thing. And I'll also adjust those as well, so they're not pins, but they have a vertical restraint on them. So during the form find, they're free to move horizontally, but they're fixed in position vertically, so they can't move back down. Now I'm going to add in, by extruding, a couple of posts down. Minus 2 meters, include beams along there. And I will also need to add in some backstays, so I'll just add on my snap grid, draw elements, and go from there down to there, and there to there. Yes, that's right. And I'll pin the base of those nodes as well. Okay, we also need properties. Let's just tuck that down the bottom. So we've got the edge tie. We also need backstay, which is going to be the same for the time being section property as the edge cables, but I'm also going to do some posts as well. I'll call it a post, and I'll add in, make it a hollow section, let's say 100 diameter, and I need to assign these properties. So element selection, pick that one, modify. I'm going to make them into bars as well, so I'm only worried about axial load, no moments. The moments they'll experience will be quite minimal, but having those bars will also help during the form find as well. And I make them property number 2, no, property number 3. And these cables here, make them into ties and make them property number 2. Note they are ties, not cables. I haven't got time to talk about cables, but they are very strange non-linear structures. If you have a look at our recording of the non-linear analysis webinar, talk about what cables do, and if you need them, they can be quite useful. But if you're not sure what they are, it will go horribly wrong. Okay, so structure in the position. We also need to set up properties. So a fabric material, so use define material, which I change from elastic isopropic to fabric, and I'll take the default properties and make sure this is assigned to my fabric. I also need to set up the form finding properties as well. Now, we're using soap film for this, so these soap film properties relate to the section properties. So this is a 1D, and so row 1 is going to be the edge, and I'll go for a pre-stress of 10 kilonewtons on that cable. The backstay, pre-stress of 20 kilonewtons, but I'm not asking for a pre-stress on the posts. Likewise, we go to the 2D soap film. We only have the one property in here, and I'll just set that equal pre-stress in the 2 directions. I'll keep this high part equal spaced. And note, of course, as well, as you can see from the coincident element markers, we've got spaces around the edge. It's coincident with those edge ties. We don't need spaces on the posts or the backstays because they're just single elements. There's no internal nodes to keep under control. Right, let's set up the analysis itself now. Close it. Now we go analysis, new analysis task, form finding, SOAP form finding, and I'll add in a dummy load case. I'm only worried about the pre-stresses in this case. If it was a larger structure, or maybe I might want to include the dead loads in here. I don't think it would be significant in my case. Let's analyze that and see if I've remembered everything. There. So you can see it's found the shape, it's offering to modify the node coordinates and to take the spacer forces and turn them into pre-stresses in the fabrics and the ties, which I want. And there is our structure, and that looks good. Note also, well, the columns are still reasonably vertical, so this coordinate at the bottom 0, 0, at the top it's moved about 30 millimeters horizontally in the two directions. So let's just modify those and free them up, because we're now going to do, as we decided we like this form, we're going to load this up with the standard load. So dead loads, snow loads, or sand if you're in a hot country, and wind loads. The dead load is easy to fall. I just use the gravity load on load case 2, and just to take a -1 factor by default in the vertical direction. This is a light structure, not too much dead load. And on the face loads for the snow and the wind, I'm going to use locate. So snow loads first of all. Global direction is projected. It's uniform in the z direction, -0.6 kilonewtons per square meter. And likewise, this is again the load up all the elements, the area elements of property 1. Wind load, which is a local load, not projected. Let's say 1 kilonewton. And note this is a local load. And if we switch on the load display, you can see that the snow load is indeed vertical, but the wind load is normal to the surface. Okay, that looks good to go. Let's create a new analysis task, which is a non-linear static. And because this is non-linear, I have to combine the loads within the analysis, so in pre-stress, dead and snow, and dead plus wind. And we could put factors on here as well as appropriate. I'm just working stresses. And let's reduce the magnification on that, because fabrics tend to move quite a lot. Okay, that's This one seems to be struggling to converge. Let's try an artificial damping, see if that helps. Yes. Okay. Wonderful. So that has converged, and let's have a look at the results. Switch the loads off and look at, let's say, displacements first of all. And we've got about 350 millimeters under deflection under wind upwards, and about 250 millimeters deflection under the snow in the middle. Now, when dealing with snow, obviously one of the dangers of snow and rain and so on is ponding, so we can look at the deformed elevation. And let's just switch off the spacers. PG1 to PG star. And we can look at this is deformed elevation. And let's see if there's any islands. I'm going to tighten up the contours in there. Let's make it a bit tighter, maybe 10 millimeters. And let's go for lines. Okay, so once you're getting quite flat in the middle, there's no sort of closed loop, so there's no actual ponding occurring under those loads. So in this particular case, we should be all right. Now, note also the results you get out also include the forces on the fabric. Let's have filled contours and set to automatic. And let's take an envelope on these as well. Let's run the wizard on this envelope. Envelope, those two cases. So we can see we're getting a warp direction stress of about 6 kilonewtons per meter width. And let's look at the projected directions. So warp direction 2.5 kilonewtons a meter, weft direction about 1.75 kilonewtons per meter. All right, I think I'm happy with that. Let's have a look at something else. So soap film summary. Got to have spacers to control the geometry during the form finding. Cable pre-stresses, you find the actual target pre-stress in the cables and also in the fabrics as well. And note that whilst I use constant pre-stress or isotropic pre-stress, you can do orthotropic pre-stress. You can have different pre-stresses in the two directions. Next method, very common method in some programs, force density. Now, force density is quite a common method for cable nets. It's also very common for sort of simpler form finding, due to the fact that you don't need to add any spacers. Now, the force density method is quite different to the soap film. Soap film, you've got target pre-stresses. The force density, you've got target pre-stress, which is based on the size of the element itself. So, if you take this example there, you've got a bar which is subject to a 30 kilonewton force, and with a different target force density on each element. The end result of the form finding is that the one with the lower force density is larger, and as the force density increases, the element lengths shorten. Of course, if you multiply this by this, you still get 30. So it does have the advantage, if you want to play around and have different force densities on different elements, you can use that to control the final geometry. And example, cable net for form finding after form finding. Okay, let me show you how to do a force density or a cable nest. That matter. Just open up a new model. I'm just going straight into a blank model, and I'm going to add in just my snap grid and just draw in a 10 meter long element. Nodes on, which I am then going to split into 10 1 meter long pieces. I then want to copy it up. Actually, if I modify that now and make it into a tie, so we can do it later. So I'm going to copy that up in this direction by 2 meters. And look on elevation, and I'm going to draw in hold the control down. I'm going to draw in my additional moments. I didn't set my defaults to ties, so they're going as beams at the moment. Remember to change those. Right, modify those ties. Okay, so that's one side. I need to copy that across to form the other side of the suspension bridge. That's good. And then if I look on elevation, I can use the volume to just look at the base part, look on plan, and then draw in. Let's set this to ties now before I forget. Draw these ties in. Nearly there. Right. Okay. And let's switch everything back on again. So properties now. Let me set up color by property so we can see what's going on. And currently everything's property 1. Now these sections, let's set up my sections and circular temporal cables. And I'm just going to copy that definition. They're all going to be 10 millimeter cables. I'm using 4 different properties because they're going to have 4 different force densities or pre-stresses assigned to them, or force densities. The pre-stresses will vary quite considerably. So let's look in elevation and start assigning these properties. So the top ones, the bottom is going to be property 1, top one's property 2, the side pieces property 3, and look and plan, the bottom ones are going to be property 4. Now these, the force density values, again, like the soap film, the rows here match the rows in here. So I'm going to set the bottom one to have a force density of 40, the next one to have force density of 10, to the top cables, and the edge side cables 1, and the base cables 1. Again, form finder, play around with these values and see what geometries it gets. I mean, design, of course, is an iterative process. Form finding even more so. Now we haven't pinned up our corners either. Pin them in position. Okay, I think we might be in a position to give this a bash now. Let's run analysis, which is form finding, force density, and a default blank load case, and analyze. And I hear Thomas sneaking in the back door. Right, so modified no coordinates, save stresses. There is our final geometry. Let me switch the references off, and we can see it has form found nicely. Elevation, you can see the lower cable, which has the higher pre-stress, is shallower. If I look at the loads themselves and annotate those, you can see we've got higher pre-stress. And if I just go property beam 1, we've got a pre-stress of about 40 kilonewtons on the bottom one, 10 on the top, near enough there. Similar pre-stresses because they're similar lengths. Look at the side pieces, you'll note that the pre-stress in the middle is about 1. The pre-stress at the end, where the cables are longer, is around about 2. The pre-stresses are proportional to the length of the element. And likewise, if we look on the base elements, as the cables get longer, the pre-stress gets higher. And if we're happy with that form find, we can just add on loads and analyze that as before. So summary on the force density, no spacers can make things a lot easier, though you have slightly less control. And you define the cable pre-stresses in the force 1D and the fabric pre-stresses in the force 2D. Note as well, of course, only isotropic force densities for 2D elements. No orthotropic properties, so you can't have the pre-stress different in the two directions. The third method we have is we call a normal property, or ignoring form finding properties. So this uses the element properties themselves. And the idea is we create large-scale deflections in the structure from applied loads. This is a very useful method for compression-only structures such as domes and arches and so on. Here's some nice modern examples, and here is an older one. This is the Mannheim World Garden Exhibition from 1975. The domes tend to be quite regular, grid shells tend to be a bit more irregular and more organic. Principles are the same in that you can have very thin elements which are mostly working in compression and have some bending capacity in there to deal with asymmetric loads, wind, snow, sand, and so on. Again, because this was about 35 years ago, the analysis was done using hanging chain models rather than the GSA as we would do today. Now this normal method is good for shell structures to create shapes which just wouldn't be feasible using the soap film type methods. Good for shells, also good for roof lattices and grillages and so on. So let us have a go at making this shell structure. And let me minimize that. And now with this shell, with GSA at this precise moment can't deal with nonlinear analysis on shells. So I am going to show you how to do a cheat, which is to use a grillage as a template. And so that we will form find the grillage, and that will give shape to the shells. And so I'll set my drawing to a quads, draw that in, and so we've got in there a grillage with a shell in the middle. So let's copy this across. That's 1 meter square, so copy it 9 copies 1 meter, and copy these up. Same again, but in that direction. And I'm just going to pin the corners, well, not the corners, the mid sides. I'm going to do it equally, but you can do it unequally as well, and see what it produces. And we also need to set up properties. So we have the grillage property, which I'm going to set up as just a concrete rectangle, nominal 200 square grillage. But so this is going to be used purely for the form finding, but the static structure at the end is going to be with the shells. And so I'm going to do it's going to be a flat shell, and its global is going to be concrete, and it's going to be just 40 millimeters thick. So it's going to be spanned 10 meters, just 40 millimeters thickness. Now, I mentioned can't do non-linear analysis on the shell elements, so what I'm going to do is set up analysis stages. So the analysis stage, first of all, is the form find. And for this stage, I will only use the beam elements. And then for static analysis, I will only use the area elements. Note, I could say all not PB1. The end result is the same. I'll also need loads to apply to the structure. Let me set my title so we can see what's going on. Dead and alive, or permanent and variable, if you prefer. And set the loads separately on the beams and the shell. So property beam 1 for the loads. Now I want live load on this, which is going to be uniform, global direction, projected Z minus 0.3, and on the shell elements, global direction projected Z minus 0.6. Oh, and we need dead load as well. So self weight, applied loads, and if we look at the stages, we can see there's our grillage for the form finding and the shells for the final condition. Right, let's form find this. New analysis, which is going to be form finding. And you know, we've got analysis stage activated, and we go form find for the stage. Ignoring form finding properties, I'm going to add in my dead and live loads, but I am going to bracket those and multiply them by a large negative factor. So I'm taking the service loads, turn them around, boost them up, and this will create large deflections upwards. Don't need to magnify that. And you see it's modified the coordinates, and don't say that it's pre-stressed. I don't want pre-stresses in this particular case. And we see there is our structure. Now the rise is a bit low on that. I want that to go a bit higher. So what I'll do is I'll just rerun that analysis second time. Again, turn off the pre-stresses, and that's a bit more like it. And we can run this several times. Each time it will deflect more and more, so it's slightly different to the other form finds. Now, if I'm happy with that, let's look at the other stage. Now, the static stage. These are 2D elements. Now, these 2D elements will not analyze at the moment. If we were to run a static analysis on this, again, take the static stage and add in our dead and live loads. In fact, let's factor those. If we try to analyze this, it will say these are warped too far out of the line. So I can double click on that to select them, and then I can just break these down into triangle elements, which of course don't warp because triangles are ultimately on the single plane. Let's just analyze that again now. So end result under factored dead and live loads. Let's look at the deflections. Less than a millimeter for a 40 thick shell. Likewise, if we look at the moments, minimal. Again, minimal. But if we look at the axial forces, this is a sort of tension. And compression. So this is a compression only shape now. Minimum tension, minuscule bending. And we can just do additional check on this, which would be a buckling check. I'll do a modal buckling on the static form. And let's just ask for, let's say, 4 modes and use the dead and live loads on here to check. Analyze that. Right, these moments won't be realistic. What we're looking for is the shape. Let's just that gives a useful. Yes, that'll do. And we can see now this is the deflected shape, but more importantly, the load factor, which is coming out just below 8. So under uniform loads, this is a stable shell. Risk, of course, is asymmetric loads. So the asymmetric loads is more likely to be the governing load case. But which asymmetric loads is down to you to experiment and find out. Okay, so normal properties in summary: no spacers, no form finding properties, and you're just using the section properties themselves to achieve large permanent deflections. So where next? If you're an Arab user, or you're an customer with a GSA fabric or a suite license, you've got the form finding, you just need to switch on and have a go. If you're an existing GSA user without form finding, talk to me or my colleagues. We can arrange a GSA suite trial for you. And if you're a non-GSA user at the moment, download the trial from the website and speak to us. The trial does not include the form finding and the fabric. It includes everything else. We can then organise a form finding license for you. So thank you very much for attending, and I hope you found it useful.